Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel for everything I want to talk about science and math. And today we are working some gas law problems. And instead of seeing me, I'm going to let you see the problems while we work through them in my calculator. Okay, so gas laws I think are pretty easy. Unless you have to memorize all the formulas, then that makes it kind of hard. But if you're taking this class with me, you don't have to memorize the formulas. You can write them on your periodic table cheat sheet. They're actually already written on the back, but in a different form, and you should write them in the form that I gave them to you. So if you look at the other sheet, it's got the formulas and you match it to it. It's exactly like that on the test. So on the test, I'm going to give you the formulas that then you can use to do your math. You have to know what they match to. Now, it's not exactly like you can't memorize B, E, C, D, F, A. I don't think. I think they're mixed up. But so you have to know what they are. Okay, so let's look at some of these problems. Okay, and one of the big things about gas law problems is that temperatures need to be changed to Kelvin first. And so what you do is you add 273. And notice that Celsius is degrees, Kelvin is just K. It's cool. It's too cool for a degree mark. It's just Kelvin. All right, so that's the only thing that's a little bit tricky there. Okay, so what you do is I want you to annotate your problem as you read it. A mixture of gases at a total pressure. As soon as I read total pressure, I know it's going to be Dalton because it's the only formula that's got total pressure. So I could go ahead and write Dalton down, and then I could put PT equals P1 plus P2 plus P3, ... As many pressures as you have.
We need all department head teachers. Please make your way up to the front office at this time. Also, a reminder, everyone, that we do have a faculty meeting at 2 o'clock in the cafeteria. Again, this is the last outcome we'll be able to make due to testing. So at this time, we need department heads. Please make your way to the front office. Thank you.
Okay, so you know I'm at school then, because sorry about that. And Miss Hepner won't know. She's on YouTube. Shh, don't tell her. Okay. All right, so you write down your formula, and then right underneath each letter, you write what it equals. So pressure total was 730. Pressure 1 was 182, and pressure 2 was 365. And then you can either write PO2 for your missing one, or you can write X. On this worksheet, I use X because we're used to X, because that's what we use in algebra. All right, so how do you get X by itself? You have to do the opposite, and it's being added to 182 and 365. So we do the opposite. We want to subtract those, and we can do anything we want in math as long as we do it to both sides. So I'm going to do 730 on my calculator. I'll go ahead and turn it on, clear out what's in there. Sorry, I didn't mean to bump y'all. Don't get car sick. Okay, 730 is on this side, and now I'm going to do minus 182. And see, I'm actually minusing it from both sides, but 182 minus 182 is 0, so I don't have to write that over there. Okay, and now I've got to get rid of the 365. It's being added, so I do the opposite, minus 365, and then there's the answer. 183, and that's our X, which is our pressure of oxygen in millimeters of mercury. Put a box around it. Okay, here's our next one. The volume of a gas is 250 milliliters. So I wrote that down and I labeled it. At 3.5 atmospheres of pressure, so I put pressure 1 was 3.5 atmospheres. What will the volume be, so question mark volume, when the pressure is reduced to 0.75 atmospheres? Okay, so now I think which formula has pressures and volumes? Why, that's Boyle's. I write it down, and underneath the letters, I write what they are. So P1 is 3.5, V1 is 250, P2 is 0.75, and V2 is what we don't know, so I write X. Now, why is X not alone? It's being multiplied by 0.75. What's the opposite of multiplying by 0.75? Divide by both sides, 0.75, and what you do to one side, you do to the other. So now I'm going to put in my calculator. I'm going to do 3.5 times 250 equals, or enter, divided by 0.75, enter, and I get the answer, 1166. I probably should have put 1167 if you look how it rounds. All right, number 3. A balloon filled with helium has a volume of 20 liters. That's my first volume. I wrote it down. And a pressure of 1 atmosphere, but later they tell us the pressure remains constant So that means it's not important, and I don't write it down. So that's clue. We don't care. It remains constant, then we don't care about it. We only care about what's changing. Okay, and a temperature of 15. So there's my 15. What will the volume be? So my unknown is the volume. If the temperature is increased to 80 and the pressure remains constant. So here's my temperature. Now, the tricky thing about this one is temperatures have to be changed to Kelvin. So 15 plus 273 is 288. 80 plus 273 is 353. Now, I write down my formula. The one that has volumes and temperatures is Charles, and then I substitute them in. V1 is 20, T1 is 288, V2 is X, and T2 is 353. You cross multiply. That means I do 20 times 353 and X times 288. Now I have this formula and I say y is X not alone. It's being multiplied by 288. What's the opposite? Divide by 288. What I do to one side, I do to the other. So those cancel out. More fun with sound effects. And now I can do this on my calculator. 20 times 353, enter, divided by 288 equals 24.5. Yay, we got it right. Okay, the next one. A rigid container of oxygen has a pressure of 3.5 atmospheres. So I write P1, 3.5 atmospheres. And a temperature of 713 Kelvin. It's already Kelvin, so I don't need to add the 273. It says, what is the pressure? So that's my question mark. If the temperature changes here. So which one is pressures and temperatures? Gay-Lussac. P1 T1 equals P2 T2. So my pressure one I put here, my temperature one I put here. X is what I put for P2 and 273. Cross multiply. So it's 3.5 times 273 on one side, 713x on the other side. Y is X not alone. It's being multiplied by 713. If a number is sitting next to a letter in math, it's multiply. So I do the opposite. I divide both sides. So my calculator is 3.5 times 273, enter, divided by 713. And there's the answer, 3.14 atmospheres. All right, moving right along. So the next one, I have a P total. So I know it's Dalton, but this time I only have two things, carbon dioxide and oxygen. I substitute in X for what we're looking for, oxygen, 520 for the carbon dioxide. Why is X not alone? It's being added, it has 520 added to it. So what's the opposite? Subtract both sides, 520. 600 minus 520 is 80. I can do that one in my head. Okay, I almost said, any questions? But if you have questions, you'll have to ask me in class. Okay, next one is our temperature is constant. That means not important. V1 is 200 milliliters. Pressure 1 is 2 atmospheres. V2 is 500 milliliters. Pressure 2 is X. Now, the units don't matter. They're as long as they're the same. As long as it's milliliters on both sides, we don't care. We just substitute it in. So 2 times 200 is 400. Y is X not alone, it's being multiplied by 500. What you do to one side, you do the other. So divide both by 500. P2, pressure 2, is 0.8 atmospheres, and that was Boyle's. Okay, our next one, we have volumes and temperatures again. So it's Charles. We substitute them in for the volume, 10 liters. But for the temperature, it's in Celsius, so we got to add 273. Volume 2 is 15. Temperature 2 is X. Cross multiply, 10X on one side, 293 times 15 on the other side. So you do 293 times 15 divided by 10. I'll do it on my calculator for you. It's pretty easy though. 293 times 15 equals, divided by 10 equals 439.5 Kelvin. If they wanted it changed back into Celsius, you would subtract 273. All right, so here's our next one. It's another Gay-Lussac. P1 over T1 equals P2 over V2. Pressure 1 is 3. Temperature 1 is 600. It's already in Kelvin. Pressure 2 is X. Temperature 2 is 400. Cross multiply. 3 times 400 is 1200. 6. 1,200 divided by 6 is 2. Almost could do that one in your head, couldn't you? 2 atmospheres. All right, so there'll be problems just like this on the test. Now, this worksheet's a little more complicated. The reason why I wanted to give it to you, some of the questions are harder than what I will give you on the test. They're more like what you would have in college, but I'll explain them to you, and just know I won't give you ones that are that tricky on the test. But the reason why I wanted you to have it is I wanted you to see the matching part, and also I wanted you to see combined gas law and ideal gas law problems. So this one is our first one. Suppose you have a volume of ammonia at a temperature and a pressure, and you need the volume at a temperature and a pressure. So this one is our P1 V1 over T1 equals P2 V2 over T2, the combined gas law. So we write it down and we substitute it in. The temperatures have to be changed to Kelvin, so add 273 to both of them, and then you just substitute it in. 760, 20, 278 equals 800 V2 over 303. So what I would do first is do this part on my calculator. So let me clear this out and you can see me put it in. 760 times 20, enter, divided by 278, enter. Now I've got this part over here to get rid of. What's making this complicated is that it's a fraction. We hate fractions. I've had some kids like fractions, so maybe I shouldn't say that. So what I say is, why is it ugly? What's making it ugly is this 303 in the denominator, so we're going to get rid of it. Because we can do anything we want in math as long as we do it to both sides. So the opposite of 303 being divided is 303 being multiplied, and what you do to one side, you do to the other. So I'm going to multiply both sides of my equation by 303. Those will cancel out, and so I'll be multiplying this number by 303. So do times 303, enter. And now I just have this part of the equation. 800 times V2. So I'm going to divide by 800 because the opposite of multiplying is dividing. And I get 20.704. And this one says 08. That one says 04. I don't know why. Just if you're anywhere in the ballpark, I'll give you credit. It might have been that I used a little bit different number in converting the temperatures. All right, number 2. Now this is the one that I want it to be all pretty and easy, but it's not, so let me explain it to you. So this one is our ideal gas law, PV equals nRT. Notice I give you the constant. It turns out there's more than one constant depending on the units that you have for pressure. So this is kilopascals for pressure. But it tells you that you're finding the volume, so you're looking for that. You're given the number of moles. The constant we're given up here, the temperature and the pressure, they tell us it's STP. Well, standard pressure is 1 atmosphere, and standard temperature is 0 degrees Celsius, which is 273 Kelvin. So originally, I was doing this fast and not paying attention, and I just put in the numbers and solved for it. And that's how you'll do it on the test. But this is actually a trickier problem because you can't use 8.31 with 1 atmosphere. They're not the same units. If you have 8.31, you have kilopascals, and you should use the one that goes with kilopascals, 101.3. You'll have one this tricky in college, but on the test, if I give you numbers, you'll just use those numbers. You're not going to have to worry about converting, okay? But also notice it says you should be able to do this in your head. What? How am I going to do this in my head? It's because of this. We know from Avogadro's number and from stoichiometry that a mole of any gas is at STP is 22.4. We're supposed to have a half a mole of it. So what's half of 22.4? 11.2. So you could actually have just skipped all the math and known the answer. But I said, but I want you to show your work. Okay, so first I did it wrong. And then I realized, oh, this is wrong. So there's 2 ways to do it right. One way is to use the correct R that goes with 1 atmosphere, which is 0.08205. The other way to do it is to just change the pressure to be the one that goes with 8.31. So I decided the better way to do it was to use the right pressure that goes to 101.3 that goes to the 8.31. So I redid it. I got the right answer, but I'll show you how to do it with the right one, the right pressure. So how we would do it is we would say let me clear it out so it's easier to see on my calculator. Clear. 0.5 times 8.31 times times, I didn't say it twice, nope, I didn't, 273, enter, and now y is x not alone, it's being multiplied by 101.3, so I divide by 101.3, and I get the right answer. 11.19 rounded up is 11.2. So on your test, you would just plug it in, but hopefully you can understand how I did it wrong and how you're supposed to do it right. Okay, this one is a similar one, okay, that it's more complicated than you need it to be, okay, in some ways, in the way I did the answer before. Okay, a given mass of helium occupies 500 cubic centimeters. That's the same thing as milliliters, so that's a volume. At 20 degrees Celsius, add 273, it's 293 Kelvin. So we have a volume 1 and a temperature 1. What volume would it occupy? So that means T2 is what we don't know at this temperature. So we have a T2. V2 is what we're looking for, T2 we have. Okay, so this one, we put it into this formula, V1 over T1 equals V2 over T2. So it equals 500 divided by 293 over X 273. Cross multiply and solve for X. So you have 500 times 373 equals 293X. Divide both sides by 293, and you get this answer, 636.5 milliliters or cubic centimeters. Now, it did not say to change it to liters, but I did. And I was just making it harder than it needed to be. There was no reason to do that, but I showed the students, I know my light went out, I showed the students how you change from milliliters to decimeters cubed. It's not just moving the decimal place over one time because it's cubed. 1 cubic centimeter equals 0.001 decimeters cubed, so you have to move the decimal place 3 places. Now, you're not really going to have to do anything that hard. I'm moving around to turn the lights back on. You're really not going to have to do anything that hard, but I just wanted to show you the math of that when you cube things, it's not simply King Henry's daughter bakes delicious chocolate muffins. Now, I know people who have gotten jobs at Home Depot, they make you do a math test, and the thing that people mess up on the math test is this idea, that when things are cubic, when they are an area, things end up being, you move the decimal place different. So if you're gonna work for Home Depot, maybe do some Quizlets on the Home Depot math test before you do it. All right, so these are some pretty easy ones. I'm going to do these quick. Here's a partial pressure one. This one, you've got P1, T1, P1, P2, P3. You don't have to solve it. It's an easier one. You just add them up and get the answer. And that was Dalton. Next one is a Boyles, P1, V1, P2, V2. You're given your first pressure and volume, your second one. So this is 30 times 1 is 30. Oops, sorry, didn't mean to bounce y'all. Divide by 5 is 6. So you probably could have done that one in your head. Here's the next one. It's a combined gas law, P1, V1 over T1 equals P2, V2 over T2. You have to change your temperature to Kelvin, but then you just substitute it in and solve for X. So on your calculator, do 95.2 times 3.2, enter, divided by 298, enter, times 273, we're going to get rid of that fraction, enter, divided by 101.325, enter, and you'll get the answer 2.75. So give it a try. If you have problems with that, I can do it slower in class. Then this one's Guy-Lussac, so you got to change your temperatures to Kelvin, put them in the formula, cross multiply, solve for x. That one's easy. Here's another one that's all complicated because of the units, because of us having an R. So this is the PV, the ideal gas law, PV equals nRT. And they tell you that you have 45 cubic centimeters of hydrogen gas. So I changed that to liters because of the unit. Then and you still need it in units. I changed the temperature to 295 Kelvin, so that's good. But then the pressure was in torr. And this 8.31 is not torr. So the easiest way to do this is to, if you want to use 8.31, is to change that torr into 101.3, into the kilopascals. So you just do 743 torr is what you're given, divided by our standards from our notes, that 760 torr equals 1 atmosphere, which equals 101.3 kilopascals. Torrs cancel out, and you're left with kilopascals. So you multiply what's on top, divide by what's on bottom, and you get, so it's 743 times 101.3, enter, divide by 760, enter, and you get 99.03. Now this could go into our ideal gas equation, PV equals nRT, 99.03 for P. Change it to liters, volume 0.045 for your volume. N is what we're looking for. 8.31 for our constant, and 295 for our temperature. So you would do 99.03 times 0.045, enter, divided by 8.31, enter, divided by 2.295, enter, and you would get the answer, which is 0.0018 mole. Now, on the test, I won't give you one that hard, but in college you will have one that hard. So it certainly doesn't hurt you to see it. On the test, you won't have to worry about units. I will give you 4 of these 5 things, and you solve for the other one. All right, so sorry that I gave you a little bit harder one. I didn't realize it until I was looking at the key, and I was like, ooh, this is a little harder than I meant. But it's fun. Hard math problems are fun. They're challenging. School would be boring if everything was easy, right? So like, share, subscribe, and have a great day. Sciences and math both are great.